All right, so let's get going on today's class. So today, for real, we're going to be taking a look at Chapter 2, the mean, variance, standard deviation, and z-scores. And specifically, we're going to spend a lot of time on this chapter because those three concepts, those three tools, the mean, variance, and z-scores, are going to be used in basically everything that we do from here on out, especially once we finally get to inferential statistics, once we get to hypothesis testing. So a lot of this is going to be at the beginning a little bit of deja vu because we've gone through the first few minutes of this last time. But regardless, let's get going. So we're going to focus today on the mean. And once again, this might not seem like the statistics you signed up for, but this is building those skills so that we have the ability to do the really cool stuff that's coming up later in the semester. So once again, keep that end goal in mind, keep that journey that you're on in mind, because the more you practice now and develop those skills, and especially the more automatic they become, the easier it's going to be later on to put them all together into these long chains that we're going to use for hypothesis testing. So once again, let's set up the example that we were going to work with. Excuse me. So let's say that you graduate from IUSB and you become an educational psychologist, and you start studying what is it about education, what changes can you make to education, what factors improve learning outcomes for students. And one of the factors that has been identified as improving outcomes for students is financial aid. Right? So we are currently in a student debt crisis. A lot of people are staying away from universities simply because of that. It's becoming less affordable for a lot of families, and it's a detriment oftentimes to students if they don't have enough financial aid. So let's say that this research gets to the governor of Indiana, and while he's working on his budget, he decides that he wants to set aside enough money so that anybody can go to higher education, so that everybody should have the opportunity to be able to go to college. So he's making this a priority, and in order to do that, he has to set aside a certain amount of money. He needs to set aside a certain allotment of funds, and what he needs to know in order to answer how much should he put aside is how much money does a typical student actually have access to? How much funds currently does a typical student have access to, whether that's through scholarships, whether that's through existing financial aid, whether that's through a part-time job, a full-time job, whether that's through support from their parents or other members of their family, wherever it's from, he would want to know how much is each student getting. And you as an educational psychologist might know those numbers. You might have done studies where you surveyed students and asked them, how much do you get per year? How many funds do you have? How much funds do you have per year in order to go to school? So you might have data on tens of thousands of students, so you know how much the typical student gets. But when you're meeting with people, they can't comprehend tens of thousands of numbers. So the last thing that the governor wants to hear is a listing of the amount of funding that every single individual has. They just can't make sense of those numbers. Our human brains are not designed to crunch that many numbers. Our human brains are designed for maybe one or two numbers at a time. So our job as psychologists in this example would be to take those thousands, tens of thousands of numbers, tens of thousands of funding amounts, and boil them down to one number that represents the entire set. And that's the key goal that we're trying to do. We don't want to overestimate what is typical of the entire set. We don't want to underestimate what's typical of the entire set. We want one number that more or less can stand in or represent the entire set of data that we have collected. So this class is going to be on the characteristics of and how to find that one number. So that one number is also known as central tendency, and we're going to take a look at the idea of the representative single score, just to shine a little bit more light on, first off, what is the goal? Secondly, we're going to take a look at 3 ways that psychologists typically measure central tendency, and those are listed in order of their popularity. So the mean, most widely used, followed by the median, followed by the mode. We're going to take a look at how to calculate those. We'll do that more hands-on next class when we do it in Excel, but this will be more conceptual. This is what the calculation entails. And then we're going to take a look at characteristics of the mean, the median, and the mode. There's 3 of them because they're different. They're good for some situations, not so good for other situations. All right, so the idea of a representative single score, we're looking at the idea of a central tendency, a kind of center of mass. It's a single score that defines the center of a distribution. And right there immediately, you can see why when I started this class last time we met, I couldn't continue with it, because in order to understand central tendency and the mean and the median and the mode, you have to first know what a distribution is. So the work we did last time on frequency distributions is going to come into play today. And you're going to see that everything that we've done so far, including summation and frequency distributions, are going to be used today to understand the mean, the median, and the mode. And then when we get to variance and standard deviation, the mean is going to be used to, and summation and order of operation is going to be used to calculate variance and standard deviation. And then when we get to z-scores, the final part of this chapter, the mean and the standard deviation are going to be used to calculate z-scores. So everything builds, which is why once I got to this point, last time I was like, whoa, because we didn't do the distribution yet. Now we did, you've been introduced to that idea. So we're looking for the one score that defines the center of that distribution. It's also the same idea, the same concept, is a single score that is most typical or representative of your entire group of scores. So your scores will always have variability in them, right? You will always have a set of scores, and most of them will be different, right? And one of the easiest ways to visualize these scores is to think about something that is very variable, very different amongst each other, and that is humans, right? So human beings are very different from each other. Everybody here is unique. Everybody here is their own individual. And if you take any 2 people, they're going to differ. They're going to differ on height. They're going to differ on level of education. They're going to differ on eye color. They're going to differ on entertainment preferences. They're going to be very different across a wide gamut of variables. Now, let's say that these people looking up at the sky are looking up at the sky because aliens are landing on Earth. So let's just say, hypothetical situation, hopefully, that aliens land on Earth, and out pops one of the aliens, and they say, you know what, we've been watching your Earth, we've seen your humans, and we really want to get to know what humanity is all about. We want to know what humanity is all about. Bring us to your typical human, right? Not the cliche, bring us to your leader. Bring us to your typical human. We want to know what your typical human is like. And, if you had to pick a typical human, it would be difficult. Who would you pick? We know who you wouldn't pick. You definitely wouldn't pick Neil deGrasse Tyson, because that's too intelligent, that's too highly educated. That would give them an overestimated view of how much scientific knowledge, for example, we have. You wouldn't want to choose Simone Biles, too athletic, too flexible, too agile. That would give them an overinflated sense. You don't want them to think that that's what a typical human is like. You wouldn't give them Hafthor Bjornsson, right? Too big, too strong, not a typical human. Nobody would look at him and say, yeah, he's kind of average, nothing too extraordinary there. So these are all atypical examples, not a representative of humanity. Who you would want to choose is you would want to choose Luke Wilson's character from Idiocracy. And if you've never seen this movie, the premise of it is he gets frozen and reawakens in the future during a time that is eerily almost like what we're at today. It was very predictive of kind of where society is going. But the key here is why he was chosen to be frozen. So he was chosen by the military as part of an experiment to be frozen. The reason he was chosen is because they gave him and a bunch of other individuals a multitude of tests. They measured their IQ, they measured their athletic ability, they measured their emotional stability, they measured personality measures, they measured height, they measured weight. They measured just about every measure that you could on a human being, and he was the one guy that came up average on every single measure. So average intelligence, average height, average weight, average athletic ability, average emotional maturity, average everything. So they froze him because he was the typical individual. He is, in that movie, the single representative score that kind of represented all of humanity. So that's the idea that we're looking for, except we're looking for it with numbers. We're looking for it with raw scores. But that's the idea, that single score that will give you an accurate idea of what all the scores are about. All right, so let's take a look at our frequency distribution that we're going to use to illustrate these ideas. So this is the frequency distribution right here, and I'll zoom in on it just a little bit and add at the x-axis there. So this is a hypothetical distribution of the amount of funding that students in Indiana have in order to go to school. So this is the amount of financial resources that they have from any source in order to go to school. So on the x-axis, sorry, the y-axis here, we have frequency. So the higher this line, the more individuals have a particular amount of funding. And the possible amounts of funding are all the way down here. So we start off at $0, absolutely no financial resources whatsoever, and we got 10,000, 20,000, and 30,000. And again, remember this frequency distribution graph is almost like an apartment building where the height of this is the height of the apartment, how many stories it has. So the higher the line, the higher the frequency of individuals, the more number of individuals have a particular amount of funding. So this is hypothetical data, but let's see what it says. First off, and this would seem accurate, there's almost nobody that has $0 to go to school. So not saying that there's not people that have very little funding, but there's almost nobody. I mean, as long as you can go to somebody and say, knock on your neighbor's door and say, can you spare $5 so I can go to school? Then you don't have $0. You got $5. So nobody has absolutely nothing. And then as you increase, say over here to $10,000, you see that more and more people have that much funding or access to that many funds, either from part-time jobs, scholarships, financial aid, their parents. Remember, this is from multiple different sources. As that financial amount increases, we get to higher and higher amounts. So a lot of people have around $15,000. And then as the financial aid decreases, we start to get smaller amounts. So people with part-time jobs plus maybe some support from other sources. We get down to here, maybe people with full scholarships. And then we have this little bump here. This would be people holding down a full-time job, maybe just going to school during the night. And then it decreases. So once you get to 30,000, 40,000, 50,000 over here, very few people are going to university and have access to $50,000 a year to do it. And then as you go on and on, the numbers drop down back to 0. So again, this is hypothetical data, but this is what we're going to use. And as you can see, there are 3 scores that have been identified here. And those are the mean, right here, just under 20,000. We got the median, right here at about 15. And then we got the mode, probably at around 14,000. So those are the numbers we're going to concentrate on today. Those are the measures of central tendency. Those are those single representative scores. So let's talk first about the one that's used the most often, and that is the mean. So the mean is the fancy word for average. This is the one you have probably encountered before. If you've ever calculated your average grade, you've calculated the mean. So the mean is computed by just summing all of your scores. So we have summation. You sum all of your scores, and then you just divide by the number of scores that you have. So if you got 10 scores, you add them all up, you divide by 10. If you're taking 5 courses and you want to find out your average grade, you add up your grade for each course, you divide it by 5, that's the mean. In this case, the mean would be a score just under 20,000. So the mean in our distribution of funding there is just under 20,000. And one way to conceptualize the mean is that this is the balance point for all of the scores. So if you were to cut this, if you were to carve this out of a block of wood, this frequency distribution, if you were to physically create a shape that looked like that frequency distribution, and you wanted to balance it on your finger, you would put your finger right there. That's the balance point for this distribution. That is where this side of the distribution would balance out the weight on this side of the distribution. So that's a clue to kind of show you the information that the mean takes in. So one of the reasons that the mean is used so often is because it uses the most information from your distribution. It takes in the most information from your distribution to figure out what is that central tendency, what is that balance point. Because what it does is it takes the amount on each side, and it also takes the distance on each side from that balance point. So you know if you had 2 weights in your hand, and they're exactly the same, you could balance yourself like this. But if you start moving one of them over here, all of a sudden it's going to tip because it's further out. So you got to move over to rebalance it. And then if somebody doubles your weight on this hand, you'll start to tip unless you bring it in, and then you can balance it again. So that's exactly what the mean does. It takes the weight of the scores on each side, and it also takes their distance into account to figure out where that central point is. All right, so for a sample, the symbol for the mean is that capital M right there. For a population, the symbol for a mean is the Greek letter mu. And a few important things to point out there. Number one, your textbook, one of the few things I dislike about the way that your textbook introduces information is that it doesn't make a big enough deal about the difference between a population and a sample right off the bat. It teaches you everything as if there's only populations first, and then later on it switches to the correct way, which is to differentiate between samples and populations. I want to make sure that we have that idea in our head right from the get-go rather than learning something incorrectly and then trying to unlearn it. So I'm going to introduce the idea of samples and populations right off the bat. I'll point out when they're important. They're not as important right now. But there is a difference between samples and populations, and you'll notice that because these two have different symbols. So the symbol for a sample mean, the mean of a sample, a group of numbers that's not everybody, is different than the mean of a population, a group of numbers that is everybody. The second thing to notice here is that the mean for a sample and the mean for a population, they get symbols. And whenever you see specialized symbols, that's an indication that what you're learning about is going to be widely used. And the sort of story I tell myself to remember this is previously the original statistical software packages. When statistical software packages first came out, they came out before the age of computers. And what they were is they were grad students that you would give a whole bunch of paper and pencils to, and you would lock them in a tower, metaphorically, and you would say crunch numbers. And these grad students, and I'm not joking, this is the way it used to be done, these grad students would have a pile of papers from experiments and from collected data, and they would just sit there with their calculator and they would do things by hand and they would have to write everything out. At some point, they were writing out mean. They were like, we got to calculate the mean, we write out mean. We got to calculate the mean, we write out mean. We got to calculate the mean, we write out mean. And these poor grad students locked in that tower started to get carpal tunnel syndrome. And their wrists hurt so bad. And one of them said, you know what? Let's just call it M. we use the mean so often, let's just call it M. Let's save our poor wrists, and we'll call the mean for the population mu. So whenever you see a symbol, know that it's a symbol because those poor grad students wrote the real words so many times that they started to develop carpal tunnel syndrome, and they said to themselves, we're using this so much, it's so important, let's shorten it. Now that's probably not a true story, but that's the way I like to think about it. So importantly though, balance point for all of the scores. It's also the most widely used measure of central tendency. So if you read psychology experiments, if you read psychology reports, you will typically read about the mean of this, the mean of those scores. That's typically the one that's used, I would say about 90% of the time. All right, the next most commonly used measure of central tendency in psychology is the median. And the median is the score that doesn't balance the scores. All it does is it cuts the scores in half. It cuts it in half so that you have half of your scores on one side of the median, and you got half of your scores on the other side of the median. So it cares about having the same number of scores on each side, but it doesn't care where those scores are. All it cares is that if it looks to the right, it sees 1,000 scores. If it looks to the left, it sees 1,000 scores. If it looks to the right and sees 200 scores, it wants to look to the left and see 200 scores. But it does not matter how big those scores actually are. So 50% of the scores are at or below the median, and the term for a sample median is the word median, and for a population, it is also the word median. So you can see that drop in importance. Not only do they not distinguish between a sample and a population, but it's not as widely used, so these grad students had no problem just writing out the word median because it's not as widely used as the mean. All right, last measure of central tendency, we have the mode. And the mode is the score or category, or in our case, the financial amount that has the greatest frequency. It's called the mode. It's kind of like the French word for fashionable, right? En mode, in vogue, or whatever. It just means popular. It's your most popular score. So that's the mode right there. It's the easiest one to see on a frequency distribution because the height of the line here represents frequency. So the most frequent or most popular score is just the peak of any frequency distribution, the highest point on any frequency distribution. The mode ignores most of the information. So it doesn't care about any of these other scores. It doesn't care about this little bump right here. It doesn't care about the fact that there's barely any frequency over here. All it cares about is who has the highest frequency. Which number has the highest frequency. So because of that, the mode is used the least often because it ignores the most information. And once again, for a sample, mode is called mode. And for a population, mode is called mode. All right, any questions so far? Alrighty. So, calculating the mean. So we're going to go through sort of the bare bones, look at how to calculate these three measures of central tendency. Next class, we're going to do this in Excel. So this is just to sort of give you a peek behind the curtain, what the formulas in Excel will actually be doing. So calculating the mean, again, you've done this before. You take all your scores, you sum them all up, and you divide by the number of scores that you have. So for a sample, the sum of the mean, that's the formula right there. Once again, just a reminder, do not read this as n equals sigma x divided by n, because that's meaningless to our minds. But if you read this as the sample mean equals the sum of the scores divided by, and n is the number of scores, so the mean equals the sum of the scores divided by the number of scores, that formula is going to make a lot more sense to you. So that's for a sample. For a population, it's the exact same idea, but different symbols. So for a population, we got mu. Populations get Greek symbols. So for the population mean, that equals the sum of the scores divided by the size of your population, and that's capital N. So N is either going to be the size of your sample or the size of your population. Either way, it's going to be the number of scores that you have access to. And that's how we calculate it, and you've probably been calling that the average, you know, for the last however many years since you learned how to calculate this in high school. All right, so that's calculating the mean. How about the median? So we calculate the median. All we want is that 50% of the scores are at or below the median, 50% of the scores are at or above the median. So for a sample, what we're going to do is we're going to take our scores. So let's say that we got 5 scores in our sample, so we have an odd number of scores. If your scores are odd, what you do to find the mean is first you order the scores. So much like we were doing ordering of scores last time with the frequency tables and the frequency graphs, you got to order your scores, put them in order. And then what you do is you find the n plus 1 divided by 2, which is the number of scores plus 1 divided by 2, which is just a fancy way of saying the middle score. So you find the middle score. So we have 1, 2, 3, 4, 5 scores here. 5 plus 1 is 6. 6 divided by 2 is 3. So we want 1, 2, 3. We want that third score. The median of this sample is 5. So the median of this set of scores is a score of 5. Because if you look to the left of 5, you have 2 scores. If you look to the right of 5, you also have 2 scores. 5 has cut this set of scores in half. If you're dealing with a population and your population is odd as well, you have an odd number of people in your population, then once again you order the scores and you find that middle score, and that is your median, and it'll have the same number of scores above it as there are scores below it. All right, so what happens though when you're dealing with a sample and your scores are even? Well, in that case, you just have to do one more little extra move. So let's say that we have 4 scores instead of 5. Once again, we order them. We put them in order from smallest to largest. And this time, we need the average of the number of scores divided by 2 and the number of scores plus 2 divided by 2. And that is your median score. So this, again, is a fancy way of saying you need the average of the first score to the right of the middle and the first score to the left of the middle. So we got 4, 1, 2, 3, 4 scores. 4 divided by 2 is 2, so we want 1, 2. We want that score right there. 4 plus 2 is 6, divided by 2 is 3, so we want 1, 2, 3. We want that score right there. So those are the 2 scores. We take the average of them. We take the mean of those 2 scores. And we end up with our median, which is 4.5. And once again, notice that we have the correct median, because if you look to the right of, or sorry, your left of 4.5, you see 3 and 4, we got 2 scores. If you look to the right, we got 5 and 9, we got 2 scores. 2 scores to the left, 2 scores to the right, same number of scores on each side, that's your median. All right, and then again for a population, if your size of your population is even, then once again we order the scores and we find the first score to the right of the middle, we find the first score to the left of the middle, we add those, divide by 2, find the mean of those scores, and that is your median. All right, and then finally, calculating the mode. So the mode is just the category or score that has the greatest frequency, the most popular, most highly occurring score. So for a sample, if you have a frequency distribution, you just find the score with the largest frequency. So if you're in a table, you just scan that frequency column and find the highest frequency, and whatever score is associated with that, that's your mode. If you're in a distribution, you just find the peak of your distribution, and that is your mode right there. So that's the same thing for a sample as well as a population. All right, any questions on the basic ideas behind the calculation of these central tendencies? All right, so why do we have three? You might be asking yourself, why is it that we have these three measures of central tendency? The mean sounds pretty good. It takes into account a lot of information. Why would we use the median that doesn't use as much information? Or why would we use the mode that ignores a lot of information when we're trying to calculate central tendencies? And one of the big issues, or one of the big things to consider when you're using these measures of central tendency is what is the shape of your distribution, and especially, do you have outliers? And these different measures of central tendency have different responses to outliers. So let's say that you're presenting data to the governor of Indiana, and he wants to know how much money, once again, does the typical student have in order to go to college? How much funding do they have access to? And what happened was a couple of years ago, let's say that Elon Musk, there he is right there, he's either going to save the world or he's going to destroy the world. He's going to do one of those two things. But anyways, Elon Musk, let's say that he visited a high school in Indiana. And he just loved it. He loved the students there. He loved the atmosphere. He just thought it was a great experience. And he said to himself, you know what? These kids are the future. I really want to make sure that they can reach their full potential. So, for everybody in St. Joseph County, when you graduate high school, you are going to get $60,000 a year to go to college. So he makes a promise that every student that is graduating high school in St. Joseph County, once they graduate high school, they're going to get $60,000 a year from him in order to go to college. So these students all graduate. Here they are right there. So what does that do to our frequency distribution? What does that do to our measures of central tendency? How do these highly funded students change the number that we would report? So let's take a look at it first without the highly funded students. So here we have our hypothetical typical data, and you can see that in this data here, we have a mean of about $18,000. And if you were to just look at this distribution and just kind of use your human intuition, that sounds reasonable, right? It sounds reasonable. You have some students that have less than that. You have some students that have more than that. But it kind of seems to be a reasonable amount to report. It kind of seems like it is a representative score. But let's take a look at what happens to the mean when we enter in, there we go, when we enter in the highly funded students from that Elon Musk philanthropy program. So these are the students that are getting $60,000 a year. So that's the frequency that of students that are getting that amount. That's the size of the graduating class in St. Joseph County. What does this do? Well, think about what the mean is, right? The mean is a balance point. And imagine that you were balancing this, on physically. And you had it balanced and you were like, yep, it's balanced. And all of a sudden a friend of yours stuck a weight way out there. Well, it's going to tip, right? It's no longer balanced. And what do you need to do in order to rebalance? Well, you got to move. You got to move over so you can rebalance the scales. And that's what the mean does. So you can see that just this little small amount of students here that are getting uber funded, that are getting super funded through this program, has moved the mean to a point at about 28,000. That's the new balance point. And that amount does not represent most of the students in this frequency distribution. You can see that most of the students are receiving less than that amount. And that's an issue. Because if you were to report this mean to the governor might say, oh my gosh, $28,000 a year? That's your typical student. They typically get $28,000 a year. I don't need to set aside any funding. $28,000, that's great, that's perfect. Problem solved. Well, not problem solved, because for most of them, they're going to have access to way less than that. And the only reason it moved there is because of these small numbers of highly funded students. So in this case, as a psychologist, you would be incorrect, and it would not be representative to use the mean for this distribution because of those outliers. So what can you use? Well, you can use some of the other measures. So here we have the median. So once again, we got the median, this time represented by Janus, the Roman god of time, looking into the past and looking into the future. Importantly for us, looking this way and seeing the same number of scores as he does looking that way. So that's the median. It wants to make sure that there's the same number of scores to the right as there is to the left. That's the median before the highly funded Elon Musk students. What happens after they graduate? Well, they come in here, once again, at $60,000. But the median doesn't care how far you are on this level of funding. All it cares about is how many people are now at this side. So it's going to have to move, but it's only going to have to move to make sure that the same number of people are on this side as there are on this side. So the median is only going to move maybe that much, right? Not a huge change whatsoever. So in this case, with these outliers here, it would be a better choice to use the median. The median is going to give you a more representative more representative score than the mean will, because you have a distribution that is sitting there with a lot of outliers. And then finally, the mode. I missed Tim Gunn. But anyways, finally the mode here, the most fashionable, popular one. We have the highest frequency score. This one is, once again, just the highest peak. We have it at about $15,000 right there without the highly funded students. What happens though when those highly funded students come into the picture? Well, the mode doesn't move at all. So the mode does not move because these students, there's just not enough of them to become the new mode. So the only way the mode moves is if another score becomes so frequent that it becomes the new most frequent score, it becomes the new mode. Outside of that, the mode doesn't care what happens out here because that frequency just is not high enough. So in this case, what you would want to do is you would want to take a look at your frequency distribution. You would want to make that frequency distribution graph, look at your data, and if you saw outliers, you would want to really think about maybe not using the mean, but actually using the median or the mode instead as your measure of central tendency. All right, any questions on that so far? All right, so let's say that Elon Musk sees takes a look at his plan and says to himself, you know what, that plan seemed a little reckless. And maybe instead of funding some students for $60,000 a year, because you don't need that much to go to school, maybe instead of funding some students at $60,000 a year, I'm going to fund way more students at a lower amount. So let's say that he changes his plan and he says, you know what, when you graduate, instead of just St. Joseph County, now it's going to be all of Indiana. All Indiana graduates are going to get $40,000 a year college scholarship. So now you get $40,000 a year to go to college. What is that going to do to our frequency distribution this time? So once again, we have our original distribution here. We got the mean, the median, and the mode, but we're going to concentrate on the mean. Balanced right there at about 18,000. Let's add those now slightly less funded, but now way higher numbers of funded students to the frequency distribution. And once again, we have now added a weight to the other side. So the balance tips, we got to move to a new balance point. And for this example, the new balance point would be approximately right there, right about 25,000. And notice that this is actually one of the funding amounts that has the lowest frequency out of the entire distribution, right? These are the full-time job students. These are the students that have part-time jobs and other sources. These are the ones probably like on full scholarships, maybe with a part-time job as well. So these are the ones that are actually the least representative amounts, right? This is the one that is the least typical, and somehow our median has ended up there. So once again, in this particular instance, because of this highly high number of outliers here, this highly unsymmetrical form of this distribution, the mean, once again, is not a good score to use. It's not representative of the sample as a whole. Let's take a look at what happens to the median this time. So last time, the median was very easily resisted the pull of the outliers. That resistance, the technical term for that is robustness. So the median is robust against outliers. The mode is robust against outliers. The mean is not robust, it's sensitive to outliers. But the median last time could deal with the outliers. However, this time, notice that it has to account for a lot of highly funded students. Last time it was able to move just a little bit because it only had to deal with a small frequency of highly funded students. Now it has to deal with a large frequency of highly funded students. And because of that, the median is actually going to move a little bit more than it did last time, because now it has to compensate for even more students on this side. It actually should have moved a little bit more. My animation quit on me. But it has to move even more than it did last time. So once again, if you have very distributed numbers of scores, the median, all it cares is same number on this side, same number on this side. But this time it's going to move a little bit more because there's more students on this side that just got added due to the high funding. All right. Last example here, we got the mode. Once again, the mode before the highly funded students is the most frequent amount of funding that is received. We add our highly funded students, and if there were more students graduating, it might have become the new mode. But because that frequency does not quite reach the level of that original peak, the mode, once again, does not move at all. Once again, it is completely robust against these outliers. All right, so any questions on those characteristics of the mean and the median and the mode? And why, when is it correct to use one, when is it correct to use the other? All right, so let's see if we can apply some of this thinking to a real-world problem, and then we'll turn it over to practice time for the rest of the class. So there has been a lot of reports, a lot of research, a lot of articles, and importantly, a lot of debate on the gender pay gap. So it's a hot button issue these days, and a lot of the debate circles around how much of a gender gap is there? What is the actual numbers for a gender gap? And I've heard numbers as low as 2% between the amount males make versus females make. So for every dollar that a male makes, females make 98 cents. I've heard that number for the gender gap. I've also heard as high as 50%. So I've actually heard people who have measured this said that for every dollar that a male makes, females make on average 50 cents. So the question is, what's going on here? Why such disparate estimates? Why can't anybody agree on what's going on? So part of it we're going to take a look at right now with some data. So this graph here comes from the Bureau of Labor Statistics, and this is women's earnings in 2016. So they have women weekly earnings, and they have women with no children, they have women with children, they have men with no children, and they got men with children. So we're going to focus on the no children examples because that's the corresponding data set I have deals with that. So let's take a look at the no children example. So we can see here that when you compare women with no children to males with no children, the women with no children earn less per week than males with no children. And it's about, what do we got, $120 less per week. So in this case, we have a gender gap, a gender pay gap, where women are earning less than their male counterparts. That's one set of data. Here's another set of data. So this set of data is the earnings of never married men and women who have never had children and are college educated and work full time. All right, so these are a little bit more criteria there, but importantly, never had children, so it's somewhat comparable to what we just saw. And notice that the yearly salary, the earnings per year, is actually higher for women than it is for males. So this data tells us that yes, there is a gender pay gap, but it's males that are actually making less than females, and it's males that should be receiving help and support to try to increase their earnings, because in the gender pay gap, it's actually men that are making less. So the question that I want to pose to you, and this is, just so that you know, this is based on U.S. Census Bureau survey of income in 2001. So one possibility, and this is the latest available data as of 2014. So one possibility that I think we can discount right off the bat is that between 2004 to 2016, there has been a massive social upheaval where men have gained in terms of the rights in our society, and it's changed from males being oppressed in 2004 to somehow males being in the driver's seat in 2016. I think we can get rid of that narrative as an explanation of what's going on. But what is going on? Why is this data saying that males are earning less, and why is this data saying that females are earning less? Any ideas?
Some of the sample size and back, but also there's just a lot of other parameters and things to consider. Like the other one had an age-specific thing. It had college degrees. This one was a lot more general.
So there was possible age-specific things. In terms of sample size, I think we can get rid of sample size because this is from the Bureau of Labor Statistics. This is from the census. This is basically everybody. So sample size, I don't think will come into this. Any other ideas about what might be going on in this case based on some of the concepts that we learned in this class? Mm-hmm.
The other one has to do only with college students. This one has everybody, right?
That's true. So that might be an indication. So that would actually say that males make more without going to college than females make without going to college. That's a possibility as well. But how about using the ideas of central tendency that we looked at today? Can anybody speculate? I'll give you one last hint. I don't think these two use the same measures of central tendency. All right, well, I won't leave you in suspense any longer, but one possibility, and this is something to keep in mind whenever you look at data, and especially if you're looking in an area and people seem to disagree, right? And this is one where people disagree, right? This is one where it's not just that it's an opinion. People can actually pull data and say, look, here's the gender pay gap. And you see this all the time. Gender pay gap, 2%. No, gender pay gap, 20%. No, gender pay gap, 50%. And part of it is the parameters that they look at. I will mention that. But to tie it into today's lesson, part of it is also what is the measure of central tendency that they're using. So I am almost certain that this measure of tendency here takes a look at the mean. And this measure of tendency here takes a look at the median. So if you take a look at the mean, it takes into account a lot of the higher earning segments of the population, and they're the outliers, right? So the individuals earning $100,000 a year, $200,000 a year, $400,000 a year, they're all the way over here, and they're pulling down that scale, they're pulling down that mean. Whereas here, we have the median. We have people on this side, we got people on this side, same number on this side, same number on that side. So what could be going on here, and something to keep in mind again when you have these disagreements, is that this might be due to the mean, where at the lower ends, we have males and females earning about the same amount of money. And this is typical of a lot of entry positions. This is typical of a lot of minimum wage jobs, right? So I guarantee you, if I ever wanted to run a study where I took a look at the wages that people were earning, and I wanted to show that there was absolutely no wage gap between the sexes, I would go to a business that had low income levels and had strict policies on hiring. I would go to McDonald's and I would take a look at their servers, their fry cooks. I would take a look at everybody there working for minimum wage. And I would say, how much do you make as a female? Oh, you make minimum wage. How much do you make as a male? Oh, you make minimum wage. No wage gap, right? It would be easy to do on the low end. One of the issues with the wage gap is that it gets larger over time. So as people earn more and more and more, the wage gap splits more and more and more, which means that on the high end, there's more males earning $200,000 a year. There's more males earning $300,000, $400,000. There's more males earning large amounts of money per year. And that number is pulling this the same way that Elon Musk's highly funded student pulled it over. That's one of the potential reasons why there's this difference in numbers, is because this is the mean. On the other hand, this is probably calculated with the median. It might also be calculated with the mode. And with the median, all that they care about is that it's the same number on each side. So the average could be higher for males, but the median actually might be smaller for males than it is for females. So once again, it does have a few more parameters, but whenever you see, and this is happening a lot in our society because people have access to numbers now, through just their online ability to access this information. They have online access. They have the ability to crunch these numbers, and you will see in debate after debate after debate, people arguing about the numbers. And a lot of times now you have the tools as a critical thinking psychologist to ask yourself, this person here says this is the wage gap. This person here says this is the wage gap. Let me stop. How did they measure it? Are they using the median? Are they using the mean? Is that potentially where it came from? So now you have a tool where you can take a look at the information and how it's calculated and know that if it's using the mean, it's sensitive to outliers. So it's sensitive to the high earners. It's also sensitive to low earners in this case. If it's using the median, it's ignoring some information. Right? Remember I told you the median is not used as much because it also ignores information. It doesn't care about the size it scores, just who's on the left and who's on the right. So a nice example, just to kind of keep that fresh in your mind, you can use a lot of and I'll mention this a few times during the semester, a lot of the tools that you use in this class, maybe you don't become an experimental psychologist, maybe you don't run experiments and analyze data using the statistical means. But you do live in a world where people are presenting you with data over and over and over again. And a lot of the tools that you have here are going to allow you to critically think about that data and think about, are they presenting it correctly? And in this case, should they be using the mean or should they be using the median? All right, so any questions or comments before we wrap up? All right, so a couple of things. I think I mentioned this last time, but for your pretest, don't forget about the Quiz Me options to earn mastery points in the MyStatLab study plan or MyLab study plan. If you're at all confused about that, check out the tutorial in the Canvas announcement. I put in a YouTube link there. It's just a little short video that tells you how to access the practice, how to access the Quiz Me, so you can earn those pretest points. And then also just a reminder that your first post-test is coming up soon to be due. So that's going to be due before we meet next class, midnight the night before. And then other than that, I am done with what I wanted to cover for today. So if you're all staxed out and that's enough for today, feel free to call it an early class. If on the other hand you want to get started on some of your homework, some of your post-test stuff, maybe some of the practice sheets, if you've been struggling with anything and want to call me over, feel free. We got about 15 minutes left today in order to do that.